Hello, apa kabar semuanya? Welcome back to my tutorial lesson, in which now we are going to talk about step-by-step approach to our last data analytics lesson, which is lesson 6, optimizing problems with simplex part 1, so simplex LP and IP. Okay, so for the sake of the outlay of the step-by-step tutorials, I would like to describe 4 different kinds of case studies. First of all, we're going to talk about simple linear programming, in which we're going to talk about wrapping paper printing business. And second is regarding blending problems. Okay, then I'm going to talk about integer programming as well, in which we're going to talk about marriage problem and optimizing the reading list. Okay, so for each problem, we will discuss a little bit of the formulations and solution in Excel. Okay, and we're going to talk about solution in Python as well, but only for the last case study, because it's complex enough and a little bit suitable to be run by Python rather than by Excel. Okay, right. So just a little bit about slight history of LP. So as you know, LP is a very good way in order to formulate optimization problems through the use of lines. So linears combined, 2 lines make a point, 3 lines make a shape, 4 lines make a maybe like 4 side shapes as a square, and then all of those given by the decision boundary, it will at the right, like for example constraints and restraints, so it will form a decision boundary shape or area, and then we use that in order to find which is a possible product mix, and then we use isoprofit lines in order to find out which one that we can leverage on hand for to maximize our objective function. Okay, so that is a little bit of summary of LP, but in terms of the history itself, it wasn't really popular until except that Danzig is actually popularizing it using the plan methods for he was actually trying to mechanize the planning process, challenged by his colleague in the US Army Air Force during World War II, and then Danzig formulated these problems using linear inequalities. But that time wasn't including the objective function, so it was very slow and there was not really things that could be used fast enough in order to generate these optimal variables. Okay, so afterwards that he included it, and then he used it as a doctorate thesis. So he received a lot of different kinds of awards from that, and he used that in order, and until now is used in operation research as the most basic optimization models. And he managed to optimize using geometry in order to find efficient simplex method. Okay, linear tools. So moving on is graphical solution method to LP, and the simplest method of George Danzig, which is very efficient. It leverages on geometry, easy to understand, and we can find optimizations of decision variables using that. So it's very simple. And of course, like Excel, it has the solver tool. It also gives us the sensitivity analysis output, which is very useful. Okay, so let us try to jump into a little bit of problem, just so that we can understand LP much better. So we have a company here, it's called Gita's Wrapping Paper. So what happens here is that she has resources. So she has paper, okay, and she has, for each of the papers, she also has the color. So he has red color, blue color, and yellow color, okay. And regarding these units of colors, it has some rules. So 3 units and 3 yellow can make the first design, 3 units 2 yellow and 3 red can be the second design. And then of course that it will have the profit, so sells at 20 per meter, 25 per meter. So let's assume that there's not cost about it, so this is profit, not revenue. So how can Gita generate the largest profit? Okay, well, so this is a little bit of outline. You have paper as your input, you have colors as your input, and finally you have outputs. So design 1 and design 2, and those have specifications what it will use, and of course it will have some profit, $20 per meter, $25 per meter that it will be sold off. Okay. Right, so the decision variables for here is nice, is that how many of the design one that I should produce, or design two of that I should produce. And objective function here is our revenue. So let's just assume that maximizing revenue is maximizing profit, so we don't think about the cost at this point of time, okay? And the constraint that we are going to use is that paper and red, blue, yellow. So you just like put down anything that you know in these three different kind of forms. So decision variables, what variable that you can control. Objective function is that what is your goal, what do you want to maximize, what do you want to minimize, so you put that here. So just note that for objective function, you need to put in one objective. So one objective for one formulation. So you cannot put like maximize revenue, but at the same time I want to minimize wastage. So you cannot do that, because by the end of the day your machine will only check one optimum variable. So how you maximize a certain thing? Well, if you want to consider wastage as well, either you put in the constraints, or maybe you make an aggregated value of it. For example, revenue per wastage, which might make sense or might not make sense depending on the case study. So you do it with due diligence, okay? Always see whether it makes sense or doesn't make sense. But for now, it's very straightforward, it's very simple. Let's just use revenue, okay? Then the constraints will be alpha meters of paper, color units, red, blue, and yellow. Well, now that we know about that, we can design it in a more subjective, objective way. So this is decision variables, D1 and D2. Is the meters of the first design, D2 meters of second design. And what we want to do is that we want to maximize the revenue. So revenue here is 20 D1 plus 25 D2. So if you remember it, is the price of design 1 and the price of design 2. Okay. And subject 2 is the constraint. So you have the constraints of the meter paper, that you have 120 people, so you can only produce D1 plus D2, the units is less equals to 120, so it kind of makes sense. Well, you have unlimited resources, so you can only produce to a certain extent. So D1 plus D2 120 is one line, so you can produce it as one line. And then the red color unit, 3D1, 3D2, 480, so you only have 480, so you have another constraint. So it's another line, okay? Then the yellow color units, 3D2, 3D1 plus 2D2 is another constraint, so you have a shape. Something like that, and then you combine with another, so you have bunch, and after that you connect it with the non-negativity, then you have a bunch of the more constraints, and after that you can formulate it into this way. So you can see here that these are the constraints, these are the constraints, these are the constraints, and the dot line is basically your objective function. Okay, so your objective is again 20 D1 plus 25 D2. So after you have highlighted those, so these non-decision boundaries, okay, and then the blue color is there, red, black, and yellow, so you find out which one is the optimum. So you see here is that your goal is to maximize the objective. So basically, if I formulate it in a geometry point of view, you can see that which one of these line is the highest. So I can do it for each of the points at the corner. So this is called the corner isoprophic method. So this is one corner here, one corner here, one corner here, and another corner here. So there are in total 5 corners. So you can do it with these 5 corners, do it here, do it here, do it here, do it here, and then by the end of the day you pick which one is the highest. So that is a very intuitive way if you want to see by picture. But of course, it's not enough, so let's do it by the Excel, okay? So, yeah. And after that, we talk about sensitivity analysis. So I did prepare an Excel sheet here. So it's very simple, put this a little bit of templates, and then, you know what, let's just do it for the next lesson. So the next lesson, I will do this, I will invite you to install an X software. I'm going to explain to you a little bit. And that will be done on the next lessons. With that, thank you so much for listening, and see you again next time. Bye bye.